Hello, and this is a follow-up to the previous video I did on manually calculating one-way ANOVA by hand. As we referred to in the previous video, a one-way ANOVA is used when we have one independent variable where we've measured more than two groups and we want to see if there's a significant difference between those groups. But we also said in that video that the one-way ANOVA is what we call an omnibus test. It just tells us if there's a significant difference somewhere between the groups, but not which groups specifically differ from each other. So we need further analyses to break that down, and that's what we're going to talk about here. What we're going to do is something called Bonferroni corrected post hoc tests, and the idea of it being post hoc is that you should only do these if you have a significant one-way ANOVA. So there's no point in doing post hoc analyses if you don't already have a significant one-way ANOVA, because there's no effect to break down. So if we look at our data we're going to use for this, this is basically the same data that we looked at in the previous video, although I've modified it slightly because we saw when we calculated it that there wasn't a significant difference in that data. So in order to be able to demonstrate the concept of post hoc tests, I basically made a significant difference between those data. And if you applied the maths I went through in that video to that data, these are the statistics you'd come up with. And we discussed in the previous video that the mean square for group is the measure of the variability that's attributable to the differences between the groups, and the mean square for error is the quite obviously the variability that's attributed to error. And from that we get an F statistic which we can compare to a critical value table, and we get a p-value of 0.001, which is less than 0.05, so significant result. Boring stuff that we covered before. So if we know that there's a significant difference somewhere in our data, how do we break that down? Well, first we need to think about the logic of all our comparisons. So we've got three groups, so what comparisons do we want to make to fully understand our effect? Well, we want to compare the waiting list versus computerized CBT, waiting list versus normal CBT, and computer CBT versus normal CBT. Those are all our possible comparisons we can do. You might know from other statistics or from my previous videos that when we're comparing two groups, we can use something called a t-test. A post hoc test is just basically a modified version of the t-test. So what is the t-test? Well, we saw that the t-statistic is simply made up of the difference between our group means over standard error of the differences, and the standard error is the slightly complicated thing to calculate. So we can fill in the top of half of our equation. Now I'm just going to do the first group here. The difference in means between our waiting list group and our computerized CBT group was 4.8. So we've already done the top of our equation, but what do we divide it by? What's the standard error of the difference? Well, in the normal t-test where we have two independent groups, there's a specific way to calculate the standard error, but in the case of the one-way ANOVA, we already have an estimate of the error in our study. If we recall this table we looked at, we saw that there's several different measures of variability in our study, including the mean square for error. And if we've already found a significant result, we don't just want to do a regular t-test, because what would be the point in that? Why did we bother with the ANOVA? Why didn't we just do it in the first place? So we want to use the mean square estimate of error variance from our ANOVA, but it's not just going to work if we put it in sort of by default. So how do we calculate the standard error of the difference? Well, this is a complicated equation, but I'm going to put it up and then I'm going to talk about it. What we do is take the square root of the measure of our error in both our groups divided by the sample size of each of our groups. Now, because we have the same sample size in each of our groups, our waiting list group and our computerized CBT group both had 5 people in it. We can already fill in that part of the equation, and because we're using one estimate of error variance, as we saw in the ANOVA video that's pulled across all our groups, we can fill that in. So the same estimate for each of our groups. So our error variance was 5.8, and our sample size in each group was 5. So we can just fill in those values, and we get a standard error of 1.523. And like we said, it's going to be the same for all of our comparisons, because the whole point of doing this is that we've already done the one way ANOVA, so we know there's a significant difference somewhere. So now that we've got that, we can go ahead and calculate our t-statistics. So using our first group as an example, we can divide the mean difference, which in this case was 4.8, by the standard error of our difference, and get a result of 3.12. We can do that for all our groups and get the t-statistics for all our groups. But we saw in the one way ANOVA video that we need to calculate degrees of freedom for our effects. That's basically the number of entities that are free to vary, and normally because we compared two things, the degrees of freedom for a t-test would usually be the total sample size minus 2, but because we used this estimate of error variance, from our ANOVA, we actually use the degrees of freedom straight from the ANOVA. So our degrees of freedom in this case, we're going to test our effects against, is the degrees of freedom for our error that we would have found from our original ANOVA. So with that information, we can compare our t-statistic to a critical value table, or go on an online calculator and get an exact significance. And we see for the first example, our p-value is 0.008, so that's less than 0.05. So we can say we have a significant difference between our waiting list and our computerized CBT. I've applied the same logic to all our other comparisons, and you see these are the values we have. For our first group we get a significant result, for our second group we get a significant result, and for our third group we don't get a significant result. So the significant ANOVA appears to be driven by the first two groups, but there's a problem with this, because the reason why we use 0.05 as a criterion for accepting significance is that we want to say we only want to erroneously accept significant results in a small amount of cases. But here if we judged these values by the 0.05 criterion, we'd be making more error than that, because we've done 3 tests, so 3 tests have an opportunity of making an error as opposed to just 1 test. Well, what do we do about this? Well, that's where the bond for only bit comes in. It's very elegant. All we do is multiply these normal p-values by the number of tests we've done, so that it puts them all on a level playing field. And if we look at that in equation form, we see that our bond for only p-value equates to our original p-value for a particular comparison times the number of tests we've done, and you can see that applied down below to the first p-value. And I've gone ahead and calculated it here in table format, and we see that our effects did indeed get less significant to compensate for the fact we've done more tests and and there's more chance we're gonna find a difference. So substantively, we see that there appears to be a difference between a weightiness group and both our types of CBT, but no significant difference between computer CBT and in-person CBT. So that was how to follow up a significant one-man ANOVA with bond for any postdoc test. Thank you for watching this video, guys, and I hope you enjoyed it. Bye bye.